Alright, time for the math. Easy solution. We're going to discuss linear approximation in physics and look at simplifying trigonometric functions into linear functions. Like say, like tan theta and sine theta, they both are roughly theta near theta is equal to 0, and cosine theta is equal roughly 1 near theta 0. This is used in engineering and optics and whatnot. This actually also uses this on the basis of designing lenses and whatnot. So basically this is used because we don't want to deal with these complex functions like tan and sine when we could just use a simple linear function when theta is really small. So I showed in my previous video what linear approximations were. Basically you can see that in the link on the info below on this. So basically you had, it's called theta there, or x in this case. Let's just call this x. Yeah, we'll deal with theta when we're using trig, but let's use x. So basically I showed if you had a curve like this, and this is f of x, and then if you want values close to, let's say, a, this one's x equals a, this is f of a, and you wanted to basically get a simple approximation for values close to it. So let's say, so values close to, let's say, here, these are close to it. This one is roughly equal to f of x, and this could be the linear approximation of L of x, and where L of x is just equal to f prime of a, or the slope at a times x minus a plus f of a. So this is basically linear approximation. Now we're going to do the same thing for these trig functions. So if we look at, let's do tan theta and sine theta together, because they're both it's going to be the same thing. They both have the same linear approximation. So if you were to graph say tan theta, let's go y theta. Tan theta looks something like this. We'll ignore as it repeats onwards, because it keeps going on as it does the same thing. So basically we'll look at only this approximation when it's close to 0. So this is tan theta, and we'll just look at this one's L of theta, or linear approximation of theta. And then similarly for sine, it's going to be the same thing except different curve. It's going to be like this. And this one's y again. Theta, this is sine theta. And here when theta is near 0, again it goes through the origin here, we're going to have L theta. It's going to be the same thing. So when we look at this one, all we got to do is plug this, use this formula for linear approximation. So we know that L theta, we'll use theta instead of x. L theta is equal to f prime at theta times x minus a plus. Yeah, this is an a actually. Yeah, so that's a not a theta, and this is f of a. And then we're looking at when, well, basically when theta is near 0, or at a is equal to 0, or this is when theta is equal to 0. So we're gonna have, so we're gonna have L theta is equal to f prime of 0, x minus 0 plus f of 0. And this one is just gonna be, well, yeah, this one's just gonna be x, and 0 goes away. So basically we know that f prime of 0 for sine theta, sine 0 is, they're all equal to tan, they're all equal to 0, so this one's equal to 0. So this is why I'm doing it at the same time, because they're all it's gonna be the same thing. So this all equals 0. And then for the derivative, we know that, let's say if f of x is equal to, let's say tan, or this is, let's put a theta here. Yeah, theta there, tan theta or sine theta. Then the derivative in this case, this one's going to be equals to, see my video on derivative of tan theta, this is secant squared theta, or in this, or for sine, we're going to get cosine theta. And then if you plug in f prime of 0, this one is just 1 over cos squared, so this is going to be 1. This is going to be 1, and cos, because cos is 1. So for both cases, it's going to be 1. And then if you plug this in here, we're going to get L theta is equal to, well, 1 times, well, this one's x, this one's a theta. My bad, this one, or you could use theta. So it's going to be theta minus 0 plus f of 0 is 0. So we're just left with theta. So the linear approximation near 0 is just theta. So L of theta is equal to theta, or this is basically equal to tan theta and sine theta. Near theta is equal to 0. Yeah, near theta is equal to 0. So I'll show you with the Excel sheet after. But now let's look at cosine. So for a cosine curve, if we look at, it's going to be something like this. It's a bit different. It's going to be like this. Let's call this y. This is x. Yeah, this is theta. So this is the linear approximation at theta. This is, let's just write this out. This is cos theta. And then from here, you could see from, well, this one, this value is just 1. Linear approximation should be just 1. But you could just, we'll just derive it the same method we did above, or linear, keep writing x instead of theta. I'll just replace it, yeah, because I'm used to using x a lot, but basically for trig, use theta is more used. So basically, to derive this one, do the exact same thing. L of theta is equal to f prime of a. Well, a is going to be 0. Theta minus a plus f of a. So just equation of a line. And in this case, f prime of a, again, it's at 0, so L theta is equal to f prime of 0 times theta, because a is 0, plus f prime of 0. And we know that f prime of 0 is just 1. So we know that f of 0 is equal to cos 0. This is equals to 1. And now to get the derivative, we know that if f of theta is equal to cos theta, then derivative, I'll just write it here, derivative of theta is equal to negative sine theta. Then if you plug in 0, this one's just negative sine 0, and this one's just 0. So then we're just, this whole thing gets out of there, so we're just left with f prime 0. So L theta is equal to f of 0 equal to 1. So this is a linear approximation. So basically, yeah, and so basically 1 is close to cos theta near theta is equal to 0. Or near, anywhere near it. Okay, so now let's compare how accurate those linear approximations were for the sine functions. For sine, tan, and cos functions, let's write x in radians here. We'll just write it as, let's say, negative 0.5, negative 0.1 here. Let's just get it smaller here now, negative 0.4. Okay, so I basically wrote a range down here from negative 0.5 all the way to 0.5 radians, and it's a bit smaller here, a bit more accurate range here, just to get it closer to 0 bits. And also, well, radians are hard to picture in my head, so I'll write in degrees actually. Degrees, just to convert them to see a better idea of what angle this is. So this, what we do is times this by the ratio of 360 degrees divided by 2 times, divided all by 2 pi. Close bracket. So yeah, so basically we'll just make this a bit more. Okay, so negative 0.5 is about 28 degrees, negative 0.1 is 5 degrees, and then from 0.05 we get 2 degrees. Basically 1 degree is roughly just a bit less than 0.02. So just to get a better idea, so now let's write all these in here. Let's write tan of x. This one is just equal to tan of this. So yeah, as you can see, it's roughly equal to that. And then as it gets closer and closer here, we'll just make it a bit there. So as you can see here, this is roughly all equal to it when we, yeah, this is rounded up a bit, but as you can see, it's really close to the value here. But then as you get higher and higher, this one's 0.45, 0.46, so it's off by a couple degrees there. Let's just write sine of x. I'll just round this up to 3. So again, this one's getting closer. This one's a bit less than that though. And then cos of x, this one is equal to cos yeah, as you see, as you get further out, it's a bit less accurate. It's supposed to equal to 1. I'll just write this. Okay. So as you can see, the closer it is to 0, the more accurate it is, and it's roughly the same. We could even look at, let's say, tan x minus x, sine x minus x. So it should be equal to 0, and cos x minus 1. So we could just go this minus this one right here, and this one is sine x minus x, and this one is equal to cos x minus 1. And now we just scroll these down. Yeah, as you can see, the tan x is more, yeah, it's closer approximation to the x value, or the theta. As you can see, that and sine, they're really close to it from a further range up, from let's say 5 degrees to -5 to 5 degrees. So as you can see, it's really close. And cosine is not as accurate, but it's still pretty accurate. From this is 1 to 2 degrees, we have 0.000 there. So it's pretty damn close. Let's just see what values does it start deviating from this. Let's write this at 0.2. Yeah, so as you see, when you get to 11 degrees, it's a bit off, or even if we go -0.158 degrees, so it's, yeah, then it starts getting off there. So basically, from around -5 to 5, it's pretty accurate for sine. If you look at these ones here, yeah, for sine and whatnot, for sine and tan, they're pretty close when it gets to 5 degrees. And cos is usually, yeah, it's more of a within 2 degrees and whatnot. Well, that's all for today. Hopefully you learned linear approximations, and if you're in engineering and this comes up, make sure you watch this video, because it's pretty important, and you'll have a better understanding of how engineering and physics and stuff, they simplify a lot of their applications using just linear approximations. Well, thanks for watching, and stay tuned for another math easy solution.